And we get introduced to the new word for perpendicular. Yay! Orthogonal is a new word for perpendicular. So these two vectors are at 90 degrees to each other in three-dimensional space. Somewhere. We don't know where. And you need to find out what the value of m is. Okay? So first of all, I sometimes find it really helpful to rewrite these as column vectors. It's much easier to visualize rather than using the unit vectors. And technically, if you write this out, you would have to have arrows over each of these as well. So if they're perpendicular, that means the angle between them is 90 degrees. And if the angle between them is 90 degrees, okay, since cos of 90 degrees is equal to 0, then you know that the dot product has to be equal to 0. Question? Orthogonal, your new fancy word. This one right here? That says orthogonal. So O-R-T with the cross being a little bit too high. Missed that one. And then the H. The rest of the letters are pretty good. I mean, basically, you could set up your formula, right? Your formula says that cos of theta is u dot v over the length of u times the length of v. And then you know the angle is 90 degrees, so then you would get 0 equals the dot product over the length of u times the length of v. And the only way that fraction is equal to 0 is if the top is equal to 0. Technically, you can multiply both sides by the bottom. And since the one side is 0, that would just go away. So now we have a new application, or an application of the dot product, is if two vectors are at 90 degrees, you know the dot product has to equal 0. So now our dot product, and this is why I wrote it as column vectors, it's really easy to multiply across. 2m times 1, m times 3m, and 8 times negative 1. We get a quadratic equation, which you can factor and solve. All right, everybody good? So in 2 dimensions, if you have the vector 4, negative 3, 4 would go on the top, -3 on the bottom. That would be your column vector. In 2 dimensions, your column vectors are very much related to your slopes. The slope of that vector would be -3/4 because your x is on top, that's your run. Your y is on the bottom, that's your rise. And since slope is rise over run, it's just going to be the flip. So if you want any vector parallel, you could choose any number in front and multiply. Put a 2 out in front, make it 8, -6. That would be parallel. Any scalar multiple. Because if you had 8 over -6, well then its slope would be -6/8, which of course reduces to -3/4. So you could choose any scalar product and multiply in front, and you would get a vector that is parallel. Now if you want something, another vector not parallel to you, technically you just have to make sure that it's not a scalar multiple. I would say if you randomly guessed 2 big numbers, you'd be like a 99% sure that you would get this right. Because if you just randomly guessed 2 big numbers, what is the likelihood that you picked perfect multiples of both 3 and 4? So any number, as long as, right? Or you could just change one of the numbers. You change one of the numbers, you're for sure not going to be parallel to what you started with. Maybe you want to make a note. There's many correct answers to this one. Now, for orthogonal or perpendicular, right, you can use your idea of slopes, right? You know that 2 lines are perpendicular if their slopes are negative reciprocals. So if I want orthogonal to you, I just think about my slope being 4/3 now instead of -3/4. That could give me a way to write, and again, maybe I write it like this, the 3 on the top and the 4 on the bottom, a vector like that. The other thing you could do for orthogonal is you could think of the dot product. So our original one was 4, -3. What would you need in the dot product to make it equal to 0? So can you see that if I put a 3 here, I would get 12. I would need a 4 there to make -12. That's not the only answer though, right? Let's say you decided to put a 6 here. What are you at? You're at 24. What would you need to make the dot product equal to 0? You'd need -24. You could put an 8. That would be a right answer. If you want to make your life a little bit miserable, you could put a 2 here. That gives me 8. What would I have to multiply -3 by to get -8? 8/3. This would be another right answer. Not as pretty as the other ones, but it's still going to be perpendicular or orthogonal to the original one. So anytime you have a dot product equal to 0, and that dot product might be really nice if you had a 3-dimensional question. Let's say I had 1, 2, 3, and I wanted a vector perpendicular to 1, 2, 3. Well, that means the dot product would have to equal 0. Can you see you could basically put any numbers in here? I'd probably start here. I'd probably say, well, let's make this 5. That's plus 15, right, in my dot product? So maybe I'd be like, oh, maybe I'll do -6 there, because then that's subtract 12. Now I'm at +3. There we go. I just made a vector perpendicular or orthogonal to the other one, because the dot product was 0. And in 3 dimensions, it's a little bit harder because you don't have that idea of the negative reciprocal with slopes. Here's our two vectors. Again, 2, x, and 1, -3. If they are parallel, well, if they're parallel, the slopes have to be the same. So we could think of the slopes. Here, the slope of this one is -3/1. This one has a slope of x/2. You want them to be the same. Can you see if those slopes are the same? What would x have to be? If you made, I mean, you could even make the equation, right? x/2 equals -3. You could solve that and get x equals -6. So that's method 1 for this one. I'm not even going to empty the boxes. We'll just talk about it. Method 1, you could think of slopes. Method 2, and method 2 is going to work with 3 dimensions as well, so it's kind of nice. Method 2 says if things are parallel, then one is a scalar multiple of the other. So we can put a variable k out in front. And if these are equal, then each of the components have to be equal. I mean, you could multiply that k through. And from here, it's really easy to see that k has to be 2. I hope you could see that k is 2 right away from the first one with the green k. Can you see that if you put 2 in there, that's going to equal? If I put 2 in there, this is also going to make x equal to -6. And the nice thing about using the variable and saying that one vector is a scalar multiple of the other vector is that will also work in 3 dimensions. So one of the things that you're going to find in vectors is there's going to be a bunch of different ways to tell if vectors are parallel or perpendicular. And so learning those techniques is going to be very helpful. If they're perpendicular, then the dot product is 0. And here were our 2 vectors, right? We had 2 and x. Is it -3 and 1? Go back to this. 1 and -3. And that dot product has to equal 0 if they're orthogonal or perpendicular. I would probably write it this way. And then I would get 2 minus 3x has to equal 0. And you get x is equal to 2/3. Or you could think of slopes. The slope of the one is x/2. The slope of the other one is -3/1. If they are perpendicular, then their slopes are negative reciprocals. So x/2 has to equal the negative reciprocal of -3/1, which is positive 1/3. Thinking that way, you could multiply both sides now by 2. And you get the same value. The nice thing about the dot product and using the dot product is it will work in 3 dimensions as well. We don't really have a skill set of thinking of slopes in 3 dimensions. Slopes in 3 dimensions would have like rise over run over, what would you call the Z? If you call the Y your rise, now what's your Z? Your depth, rise over run over depth? And have like this triple fraction thing? Gets complicated. So then your vector math becomes easier to use. So given that 2 vectors are perpendicular or orthogonal, find the possible values of the constant t. Okay, first of all, I'm going to write out both of these vectors. This one is going to be 3t plus 1, and then a 1, and then a minus 1. Here we have t plus 3, and then a 3, and then a negative 2. Writing the column vectors just makes the dot product easy to see. Because you need to multiply the corresponding, so here in purple, this one times this one, that shows up right here. In orange, this one times this one, shows up right there. And finally in light blue. And if things are perpendicular or orthogonal, then your dot product is equal to 0. If you forget that, you could go back to your main formula for the angle between and plug in 90 degrees for theta and solve from there. And it will do the same thing as telling you that the dot product has to equal 0. So once we set that up, now it's just a matter of solving for t, combine your like terms, factors nicely,